Hello, I'm Yupan Liu. I'm going to present my results, StoqMA meets distribution testing, and the paper is available on arXiv. So what's the complex class StoqMA? We're starting from a quantum definition of NP. Consider language L is in NP. There's a verifier such that for any input X in L, a polynomial time verification circuit Vx such that for yes instance, there's a witness, Vx accepted. For no instance, Vx rejected any witness. Why we said it's a quantum definition? Because we willed Vx as a quantum circuit, namely a verification circuit using only classical reversible gates, such as Toffoli, C0, and X. Also, we measure the designated output qubit in the 0-1 basis. So here we have acceptance probability. It's a squared L2 norm of this vector that starting from cat W and 0 and theta, and first apply Vx, then apply this projection of cat 1 on the first qubit. Why our definition is equivalent to the standard one? It seems we even can use quantum witness here. The reason is, if we think this acceptance probability as a projected form where the left and the right vectors are both the witness, cat W, then the matrix here is diagonal. So the optimal witness is classical witness, and our definition is equivalent to the standard definition. Now let's move to MA. Consider a promise problem in MA. There is a randomized polynomial time verification circuit Vx such that for each instance, there is a witness. Vx accepts this witness with probability at least 2/3. For no instance, Vx accept any witness with probability at most 1/3. Since we are adding randomness here, we need a different kind of ancilla, namely cat plus. It is a uniform superposition between cat 0 and cat 1. Also, we are allowed to use at most polynomially many such ancillas. Similarly, we have an acceptance probability for MA, and here we have this plus ancillas. There's a new phenomena for MA called error reduction. Just consider an MA verifier such that for yes instance, acceptance probability is at least A, and for no instance, acceptance probability is at most B. As long as the gap between A and B is inverse polynomial, we can make the threshold parameters A and B to be exponentially close to 1 and 0. Then by choosing some good parameters, we can replace A and B by 2/3 and 1/3. How do we prove it? Just run polynomially many copies of the verifier in parallel, then we can take the majority vote of the measurement outcomes. Okay, now let's move to the class StoqMA, which is originally defined by Barry, Besson, Tahal. Consider a promise problem L in StoqMA. There's a verifier such that for any input X in L, a randomized polynomial time verification circuit Vx that measures the designated output qubit in the plus-minus spaces, such that for yes instance, there's a witness, Vx accepts this witness with probability at least A. For no instance, Vx accept any witness with probability at most B, where A and B is between half and 1, and the gap between A and B is at least inverse polynomial. So here we have a acceptance probability for a StoqMA verifier, just to replace the projection of cat 1 on the first qubit by a projection on cat plus. We have a few remarks on StoqMA. First, threshold parameters A and B cannot be replaced by some constant since error reduction for StoqMA remains unknown. If we just do the parallel repetition for StoqMA, then for each copy of the verifier, we need to measure the output qubit in the plus spaces. But in the definition, we only can do this kind of measurement once. So it's not surely true. Second, for any non-negative witness, by some straightforward calculation, we can see the acceptance probability is at least half. Third, thanks to this Perron probability theorem, if we think the acceptance probability as a projected form, then the matrix here indicates that the optimal witness is non-negative state. So without loss of generality, we can think the witness as a probability distribution. then what's the computational power of StoqMA? Brownie Besant defined this class to capture the computational power of the stochastic local Hamiltonian problem. So just the local Hamiltonian don't have the sign problem, namely, think about this exponential size matrix, and each entry of this matrix is just a non-positive. Such problem is StoqMA complete. Also, StoqMA appears in this complexity classification of two local Hamiltonian problems, which is by Qubit Montanaro and Berry-Hastings. So such problem is either in P or NP complete, or StoqMA complete, or QMA complete. It's a quantum analog of this Schaeffer theorem of CSP. Regarding the lower bound, it's easy to see that StoqMA contains MA. Just by simulating a single qubit 0-1 basis measurement using a single qubit plus minus basis measurement with an ancilla qubit. For the upper bound, we can show StoqMA is containing AM, essentially SPP, where AM is a two-message generalization of MP, and the proof is using the set lower bound protocol by Goldwasser-Sipser. Breuer-Besant also showed that StoqMA1 is equal to MA. So just StoqMA with perfect completeness. Under generalization assumption, AM would collapse to NP. So all the class we mentioned here, MA, StoqMA, and SPP are supposed to be the same. So the question is, it is possible to collapse the hierarchy. MA is containing StoqMA is containing SPP. So now we are going to present my first result. Before the result, we need some basics in distribution testing. So first is this sample assessors. Consider a fixed distribution D over omega, then a sampling oracle for D is an oracle SD. So when we call this oracle, SD simply returns an element X in omega with probability dx. The task we consider here is called tolerance testing. So just given independent samples oracle assesses to unknown distribution D0 and D1, decide whether they are epsilon close or epsilon far from each other. And once the result is useful for us is sample complexity lower bound for distribution testing in squared Hallinger distance. It was shown by Daskalakis, Kamas, and Wright. So the squared Hallinger distance here between two distribution D0 and D1, just 1 minus the inner product between D0 and D1. So task here is they also show any algorithm for distinguishing the squared Hallinger distance is between D0 and D1 is either smaller than epsilon square over 8 or larger than epsilon square over 2, where epsilon is a constant, requires n over log n samples, namely the sample complexity is inherently depend on the dimension of the distribution. Could we use this distribution testing technique to show something for StoqMA? Now let's just revisiting what happens before the measurement. So let the state before the measurement be cat 0, cat D0 plus cat 1, cat D1. Then we measure the designated output qubit in the plus minus spaces. So what happens here? The acceptance probability here is equal to half plus the inner product between D0 and D1 is equivalent to 1 minus the square Hallinger distance between D0 and D1, where the squared L2 norm of D0 plus squared L2 norm of D1 is equal to 1. So to show StoqMA is containing MA, it is sufficient to approximate a squared Hallinger distance between D0 and D1 within 1 over polynomial accuracy using only polynomially many sample sizes to D0 and D1. Why is that? because each sample will draw it by just run a copy of the verifier and measure all the output qubits. So polynomially managed sample means that the new verifier we have just have a polynomial factor of the original verifier. Therefore, it seems we can prove in MA containment by distribution testing. However, if you still remember this sample complexity lower bound we mentioned before, this kind of MA containment requires exponentially many samples. So the new verifier will have exponentially many exponential size, and that's not good for us. But we still have some good news. We probably could take advantage of other models. That's our first result. StoqMA is contained in MA, where StoqMA is a subclass of StoqMA. So what we need is a dual access model defined by Canoni and Rubinfield. First, we need sample accesses to D, where D is just a distribution generated by the witness and the verifier. Just run a copy of the verification circuit Vx that takes W and their ancillas as an input, then measure all qubits in the 0, 1 basis in the end. Here we willed the measurement outcome I, which is an n-bit string, as a sample. Also, we need this query accesses to D0 and D1. D0 just defined by the distribution D, where any index is starting from zeros, and so does D1. So given index J, which is an n-1 bit string, there's an efficient algorithm QD evaluates the quotient D0J over D1J. And there's a result by Canoni and Rubinfield. They show that approximating the total variation distance between D0 and D1, which is almost the square Hellinger distance, within epsilon accuracy requires only 1 over epsilon square accesses to the oracle. So if the epsilon is just the inverse polynomial, then the number of samples we need is just a polynomial. So we're able to define its StoqMA, namely StoqMA with easy witness. Easy witness just defining this way. Given a non-negative witness state D, there is an algorithm QD such that the quotient D0J over D1J can be efficiently evaluated for any index J. For instance, consider a subset state where a subset S here, the membership of it is efficient verifiable. Since in our definition, we don't care about the cardinality, we only care about the quotient, such a state is exactly an easy witness. And then we can define StoqMA. Just for each instance, the witness here must be easy witness. Now let's prove StoqMA is equal to MA. So first, MA is contained in StoqMA is easy. Why? Because first, classical witness is easy witness, and second, MA is contained in StoqMA. So it's sufficient to show that StoqMA is contained in MA. Here's the proof. Consider a state before measurement, namely cat 0, cat D0 plus cat 1, cat D1. Then acceptance probability over the L1 norm of D1 can be written as an expectation over a normalized distribution D1 of the one variable, which is the square root of 1 plus D0I over D1I. Notice that the quotient D0I over D1I is efficiently evaluated by the algorithm QD guaranteed by the property of easy witness. Also, we can draw a sample by just running a copy of the verifier and measure all the qubit in the 0, 1 basis in the end. So by Chernoff bound, a numerical estimation infers that a Newton's polynomial additive approximation of acceptance probability, then we finish the proof. As a corollary, we have a simplified proof that StoqMA1 is contained in MA. So it's sufficient to show that StoqMA1 is contained in StoqMA. And the proof is using this StoqMA1 complete problem, namely SSP. So we have an exponential size configuration graph, and each node is either marked good or bad. Also, we can check whether a node is good efficiently. So the easy witness here, just a subset state associates the state that consists of all nodes that mark good. Interestingly, Brary also proposes guided stochastic local Hamiltonian, which is containing MA and is a subclass of stochastic local Hamiltonian. This kind of stochastic local Hamiltonian can be revealed as a generalized Hamiltonian version of StoqMA. Now let's move to my secondary thought. Namely, a new StoqMA problem comes from distinguishing reversible circuits. The starting point is swap test. So swap test is used to distinguish two states psi and phi. Swap test outputs 1 with probability square of the inner products between psi and phi. Just think the psi times phi as a witness, then swap test looks like a trivial StoqMA verifier with maximum acceptance probability 1 and optimal witness is classical. Within the fashion of swap test, we can define this problem reversible circuit distinguishability. Given two efficient reversible circuits C0 and C1 that utilize the same number of ancillary states cat 0 and cat plus, where the number of cat plus is n plus. Let non-negative states generated by Ck and the given witness cat W be dk, namely dk is equal to Ck apply on cat W, 0 ancillas and plus ancillas. Decide which is the following case. For yes instance, there is a witness such that the inner product between D0 and D1 is at least A. For no instance, for any witness, the inner product between D0 and D1 is at most B, where the gap between A and B is at least inverse polynomial. Here's the result we have. First, the mean theorem is reversible circuit distinguishability, namely with polynomially many plus ancillas, is StoqMA complete. It's a bit surprising because distinguishing quantum circuit is StoqMA complete. Also by Jordan, we know distinguishing reversible circuit without ancillary random bits, namely plus ancilla, is NP complete. So this problem seems to be MA complete, but in fact, it's StoqMA complete. Furthermore, we show that exact reversible circuit distinguishability, namely the inner product in the no instance is 0, is NP complete. Essentially, what we show is StoqMA with perfect soundness is containing NP. This property is known for as a Merlin game. So for any as a Merlin game with perfect soundness, will collapse to NP. Also by Tanaka, we know exact quantum circuits distinguishability is complete for QMA with perfect soundness. Moreover, we show that reversible circuit distinguishability without any ancillary random bits, namely n plus is 0, is NP complete. Now let's prove to the StoqMA completeness. So the proof let's remember the decay, where k 0 or 1, defined by Ck applies on cat W, 0 ancillas plus ancillas. So first we need to show RCDs containing StoqMA. Here's the construction. We're starting from a state, which is cat plus, then first run the control C0, then flip the first qubit, then run the control C1, then the state before the measurement, namely the dashed line. What we have is uniform superposition between cat 0, cat D0, and cat 1, cat D1. So by straightforward calculation, we know it is indeed contained in StoqMA with completeness half plus A over 2 and the soundness half plus B over 2. Then we need to show the StoqMA hardness. We are using the same gadget here. Just set C0 to be the circuit that first apply Vx, then flip the first qubit, then apply the Vx dagger, and that C1 just to be identity. So what we have now is a simplified gadget. Then using this matrix, M comes from think the assumptibility as a projected form, then we know the assumptibility can be written as half plus half times the largest eigenvalue of m. Using this, we can show, given any StoqMA verifier, we do have RCD instance. And this observation regarding this m can went back to the weak error reduction for StoqMA by KTF. Okay, now it's my third result. It's about error reduction for StoqMA regarding soundness. So why is even error reduction important for StoqMA? So here's a conjecture. If we do have error reduction for StoqMA, it should look like in this way. So for any AB between half and 1, such as the gap between A and B is at least inverse polynomial, then StoqMA with completeness A and the soundness B is contained in StoqMA with completeness 1 minus 2 to the minus n, and the soundness half plus 2 to the minus n. Namely, the threshold parameters can be made to essentially close to 1.5. And my result here is we can do the error reduction for the soundness side. Namely, for any L, which is a polynomial, StoqMA with completeness half plus A over 2 and soundness half plus B over 2 is contained in StoqMA with completeness half plus A to the L over 2 and soundness half plus B to the L over 2. So if A is 1 or very close to 1, then we can reduce the soundness error. So to show us the error reduction for StoqMA, it suffices to reduce the two-side error separately and alternatively. Namely, first reduce the confidence error, then reduce the soundness error, or then reduce the confidence error. There are a few procedures using this way to do error reduction. For instance, this polarization of SAK or space-efficient error reduction for QMA. So could we do this confidence error reduction? Since first we don't know how to do it, and by my another result joint with Harov and Grillo, we know if you can do the error reduction regarding the confidence, then it implies that StoqMA is contained in MA. Okay, now let's prove the error reduction for StoqMA regarding soundness. Okay, now let's prove the theorem. As a corollary, we know StoqMA 1 have an error reduction. So here's the proof. Now we are using the gadget used in the StoqMA harness proof of reversible circuit distinguishability. So the acceptance probability of this verifier using this gadget is half plus half times the largest eigenvalue of m, and m is writing in this way. Notice that it's using a control qubit, so we can just do the parallel repetition, and for each run of the verifier, let them share the same control. So in the analyze, we just take the tensor product, or you can think about it as a conjunction or AND. So for this new verifier, Vx prime, the maximum acceptance probability that Vx accepts W1 times blah blah times WL is equivalent to half plus half times largest eigenvalue of m to the L. I'm talking about tensor product. It's equivalent to half plus half times largest eigenvalue of m to the L. So we are done for yes instance. For no instance, it seems entangled witness would increase the maximum acceptance probability, but in fact it's not. The reason is the largest eigenvalue of the tensor product of matrix is equivalent to the product of largest eigenvalue of matrix. And same trick also used in the analysis of the weak QMA error reduction by KTF. Now we move to the open problems and the summary. So the take-home message in my talk is the difficulty of StoqMA arising from different kind of optimal witness. So if the optimal witness is classical witness, then by short proof by Grillo, we know that 6 StoqMAs contain MA, and this proof preserves completeness and soundness parameters A and B. Namely, if the gap, even the gap between A and B is eventually small, then we still have this inclusion. Then, if the optimal witness is easy witness, then by the theorem in my result, we know as long as the gap between A and B is inverse polynomially small, we know StoqMA is containing MA, where MA have the gap is just a constant. If the witness, the optimal witness is non-negative, then we still don't know how to show StoqMA is containing MA. Second, soundness error reduction for StoqMA is possible. Namely, when the completeness is almost 1, then we can do error reduction for soundness. And interestingly, the proof is inspired by showing distinguishing reversible circuit is StoqMA complete. And this problem seems to be MA complete, but in fact, StoqMA complete. And then it's open problems. The first is how to show StoqMA is equal to MA or SBP is equal to MA, which is much stronger. The second question is, could we do the error reduction for StoqMA regarding the completeness error? Namely, if soundness is very small, could we reduce the error for completeness? The third one, could we find more natural StoqMA complete problems? That's all. Thanks for your listening.